Test methods performed by the powder characteristics tester include cohesion, uniformity, and dispersibility. I'll talk about uniformity first because that may be the bulk test that's used for a number of powders. In order to perform the uniformity test, what we need to identify is the D10, which is the diameter at the 10 percentile, and the D60. Once again, I'll say 60. So that's the diameter at the 60 percentile. Those two micron sizes are actually inserted in fields that will then calculate what the particle size uniformity is of that particular sample. Now, how does that relate back to cohesion? Cohesion relies on the mean bulk density of the sample. What is the mean bulk density of the sample? The mean bulk density is the aerated and the packed. It's divided, add them together, divided by 2, and that's my mean bulk density. In Carr's test method, he's defined 3 levels. The first level is less than 0.4 grams per cc. The next is between 0.4 and 0.9. And then there's greater than 0.9 grams per cc. And what I'm referring to here is a chart that will simplify those actual values. So let's take, for example, if your sample has a mean bulk density of less than 0.4 grams per cc, and, this is another critical part, is less than 150 micron, you then can perform the cohesion test utilizing the recommended sieve screens. So in that case, it would be 350 micron, 250, followed by 150. The critical part here is well defined. It's got to be less than 150 micron, is that 100% of the material must pass through the finest screen. Now, why do we do that? Simply because we want to identify the natural attraction or cohesion of particle to particle. The next level would be the 0.4 to 0.9, 75 microns, so then it's 250, 150, and 75. And then greater than 0.9, 100% must be less than 45 micron, so then it would be 150, 75, and 45. Please note that the higher the bulk density, the finer the particles. So from that aspect, if you know your mean bulk density, because the finer the particle, the greater the surface area, the greater the surface area, the higher the potential for cohesion. So what we're trying to identify is that level of cohesion. Now, what if we don't meet that criteria? Well, as I just mentioned about the uniformity. So if it's greater than 150 micron, what we then need to do is the particle size uniformity, at which time the D10 and the D60 come into play. So you have 150, 75, and then 45. Now we'll demonstrate performing the cohesion test utilizing the powder characteristics tester. We're going to assume that the bulk density, the mean bulk density, is less than 0.1 gram per cc, which would put us into the category of the 0.4. So what we'll do now is we will press the icon that opens up the explanation of the cohesion measurement which I've just gone through. It'll give you an explanation. However, in this case here, it's just reiterating what I had indicated previously. Now, this is a chart that allows you to confirm the variations. There are some cases here you might see 355 micron versus 350. It's such close proximity, it's not a major catastrophic issue, so it's either 350 or 355. It will also identify then what the micron size range is of the top screen, the middle screen, and the bottom screen. So we'll press next to proceed and advance. We're going to correlate the weights utilizing the balance that's communicating with the entire system. So now we're going to tare the balance, at which time we're now going to take the bottom screen. However, what I like to do, which we'll see in a couple of slides further along, is I like to place the screens in their proper location. So we'll go through it, but there's certain apparatus that we must put in place. We must put in the sieve holder in place. And now what we can do is we can take and measure the screen. So we'll take the bottom screen, place the bottom screen on the balance, and press next. You'll see that when it's stabilized, it gives you the weight. We then place the screen in the holder. The next would be the middle screen. In this case here, as we're simulating 75 micron, we place it on the balance and stabilizes, and we take that. Now what we do is we nest the screens together in the holder. Pressing next, we now take the top screen, place this top screen on the balance, it stabilizes, and notice the weights have all varied to some degree. And we now put that in place. So we press the next button. Once again, when we move along further in the software, it's going to give you a better pictorial as to how to assemble it. But I like securing things because what happens here is that you move along and then you're not secure, and the software seems to leave you in the lurch there, and it doesn't give you that guidance. So what I did was I put a cup extension, which is a modified cup extension, and the clamp into place. I will also place this collection pan here so that any material that passes through the screens does not fall throughout the machine. So what we'll do now is we're going to place, instead of weight paper, a small little sample bucket on the balance. We're now going to tare it as if there's no weight there. And in this case here, the software indicates that we want to take a 2-gram sample. What's nice about the PTX, we have the flexibility with the PTX and the software to be able to vary the sample. So what we'll now do is we'll just take some of this material and we will measure it out. Oh, I've gone way over. So let's take some of that out. We got 5.88 grams. Now, in accordance with the official Carr paper, it's a 2-gram sample. However, because of the mathematics, due to the electronics and the software and et cetera, we can actually vary the sample. So what we'll do is we'll press next. And notice it's going to stabilize at 5.8, and it gives you a confirmation that you're dealing with 5.88 grams. All right, so we'll press next to proceed. As I mentioned earlier, here is the assembly layout. We've gone through that. It may be a little bit premature, but it's all set in place now, so you can proceed to the next step by pressing next. Based upon the mean bulk density, the amplitude of vibration and the sieving time will be calculated. So what we're going to do here is we're going to use a 1 millimeter amplitude, which is going to be electronically controlled, that can also be confirmed by means of this gauge that's located on the front of the vibratory platform. It also has the second, so we'll now go to press start, but there was one minor thing. The software has a minor little step in there that's missing. It didn't tell you to charge the material. So what we're going to do is we're going to put the material in. And notice already that some of the material is passed through. I don't know if you can get a close-up on it, but if you can, that's great. So we're going to press start. We've always got to be closing, for safety purposes, the cover. And now what will happen is the vibration will begin. Notice how the material is passing through. It's not that cohesive. Now, in this case here, you're not able to make any adjustments in the vibration. Notice these arrows have been grayed out. So we'll allow this to time out, which is very close to that now. We've got 7, 6, 5, 4, 3, 2, 1. everything shuts down automatically, and the software advances to the next step. So we now unclip the stack, set the clamp aside. Meantime, we could have actually been tearing the balance, so what we're going to do now is we'll tear the balance, and then we take the top screen. So in this case here, we have the top screen. We weigh it. Okay? It gives you a display here of how much sample was retained on it. Okay? Then we go to next. We take the middle screen, place the middle screen on the balance. Okay. Lastly, we take the bottom screen. Now you can take this entire stack out. Again, that was a holder. Set that in place. And what I'll do is press next. And here's the bottom screen. Next. Okay. So this is going to describe what's actually taking place. The retained sample on the bottom screen weighed out at that percentage. And what we're going to do is we're going to calculate the overall cohesion in this case. So there was no material retained on the top screen. There was 1.6 on the middle, 1.85. So what this is going to calculate out to is a total cohesion value of 22.7%. Again, this is simulated, so I don't want anybody to take this as gospel, that when you're dealing with this green type of powder, that you're always going to get that result. It also relates then back to the 12 Carr index. So what are we going to do next? Well, in order to satisfy the entire battery of tests, we now need to do the dispersibility test. Dispersibility, what we're going to do is drop a sample onto a pre-teared watch glass. So in order to do that, what we need to do is we need to measure or weigh the weight of the watch glass. So we will now tear the balance once the screen has been removed. Okay. And place our watch glass on the balance. We now get the weight of the watch glass. Okay, which in this case here it's 43.96. Next. Prior to doing that, what we're going to do is place the watch glass in its location. I'm going to lower the screen just for a moment here so that you can see where the watch glass will be placed. And I apologize for my stepping in front of the apparatus, but what we'll do is we'll just put it in place. So as you can see, there's a holder here. The watch glass has a ring on it, and we set the watch glass in place. We then slide it into the cavity, which has a perfect alignment for it, and then what we'll do is we'll close the lever. Now, there'll most likely be a slide in here that will give us those kind of instructions, but in this case, again, like in the past, I like to place things in order so that we can just proceed through the test without any fear. One other thing that you should also recommend is make certain that the gate is closed here. There is a gate here that has an opening that you can see will pass. It works in a counterclockwise rotation. Okay. So now what we'll do is we'll then again tear the balance with the sample holder in place. And in this case here, we take a 10-gram sample. But as we did previously for the cohesion test, it's not mandated that it be specifically 10 grams because of the electronics involved. So what we'll do is we'll now take this. I'll just dump some in there. 28 grams, which is a bit extreme. Well, I didn't take much out, did I? Okay, so we're on with 18 grams, which, because this material is rather dense, it looks, and we'll just take the weight of that by pressing next. Okay, once again, to advance the software. Like I mentioned earlier, now what it does is it shows you where to put the various componentry. We've already done that. So what I'm going to do is I'm going to advance the software so you can have a little better idea as to the gate must be closed so that we can now feed the sample into the cup. All right, and I am going to advance the software one more time, but I'm not going to tear the balance until after we've dispersed the product. So I'm going to close this down so you get a better idea, and then I will charge the cup. So it's very important that you close that gate before you go through the process. Now, once I open this gate, it's going to have a snap action open. The product will fall and it will be collected on the watch glass. The intent here is to determine how much material actually is collected on that watch glass. Now, what occurs is you not only have the product falling, but you also have the product slapping against the glass or splashing. That's all taken into consideration during this test. So, are you ready? It might be a little fast. Okay. That basically has performed the test. What we'll do now is, and I do not want to, but if you can take I'll have to show it to you after I take it out, only because if I tilt this, I'm going to lose the product. So let's just do this once again. And my apologies for the back. We'll tear the balance. We'll remove the watch glass, and as you can see, there's quite a bit of material on the watch glass. Place it on the balance. Press next. Okay. And it'll tell us what the total weight and the sample weight was. And in this case here, 16.7% dispersed. Now, as I mentioned a little bit before, I can show you, notice how much of the material was splashed as it fell. That's also taken into consideration as far as the dispersing property of the product. Okay. Progressing. What we'll do now is just press next to proceed. And notice, all of the icons have become gray. That's an indication that all those tests have been performed. We can now save and close. Okay, so this is another step that we didn't get involved with, but this is how we register and file all of the tests. As mentioned earlier, Ralph Carr developed the methods, however, for those products that were outside the parameters to perform cohesion, you would perform the uniformity test. And the uniformity test requires that you determine the particle size, 2 points, the D10 and the D60, and then simply add those into the software. So, as we see here, the cohesion, uniformity is the D10 divided by the D60. So what we'll do is we're just going to pick some arbitrary numbers. We'll pick, let's say, 25 micron for the D10, and what we will do is we will use just an odd number to give it a little bit of a twist, 63 micron for the D60. So these are just arbitrary values. They have no correlation to any of the tests that have been performed. We calculate it, and it shows that it has a uniformity of 2.5%. Quite frankly, that's taken into consideration to then identify what the overall Carr index values are that can help and guide you through the determination of the flowability of a product and the floodability of a product. Thank you.